What is up, everyone? Hope everyone doing well. On this video, I'm going to talk about a Taylor series. Yes, suppose we have a finitely many differentiable function. So not infinitely many differentiable function. So this time we have a finitely many differentiable function. That means we can find a Taylor polynomial like this because it has only finitely many derivatives. So suppose this is differentiable, this function is differentiable how many times? So n plus 1 times. So this function f here is differentiable n plus 1 times, right? So now we find the nth order Taylor polynomial of f around a. So this is the nth order Taylor polynomial of f around a, right? So here, so this is nth order. Here, look at this is the maximum power of the maximum degree of the maximum exponent is the degree of the polynomial. So maximum one is n. This one is nth order polynomial. So this is called nth order nth order Taylor polynomial. We denote that one as t sub n of x, right? So we know that if the function is infinitely many differentiable, the Taylor expansion converges to f. But in this case, right? So this is a polynomial, right? Because this function f is finitely many differentiable and plus 1 times differentiable. So because of that, we just can only find the nth order Taylor polynomial. So there's a difference between the real actual function and the nth order polynomial. So this is a kind of error. So this is the remainder. Some people say this is the Lagrange remainder, right? So some people say this is the remainder of Taylor series. So this is a kind of error. So this is the error between the actual function and the Taylor nth order Taylor polynomial. So here we have a function. So this this one is the nth order polynomial. So which is something like this. This is evaluated. So nth order polynomial around a, centered at a. So something like this. When you go further from this point a, you get some error like this here. So the distance between the actual function and the Taylor polynomial can be evaluated, right? That's why we are going to try. So we are going to find an error bound for this nth order polynomial. So nth order Taylor polynomial. So what happened when the function is infinitely many differentiable? That means, so if the function is infinitely differentiable, then you can find the real Taylor expansion centered about a, around a. So t of x, so we have learned t of x is the Taylor expansion around a, right? So here this one. So in this case, the function is infinitely many differentiable, right? Differentiable. Then you can find the Taylor expansion. this Taylor expansion converges to f of x in the given over the interval. You can find that interval, this one converges to f of x over the interval x minus a less than r. So this r can be computed by using ratio test, right? So using ratio test, you can evaluate this r, then you know this radius. Then you can find the interval of convergence. So over this interval, this infinite series or this Taylor expansion converges to the function f. That function is infinitely many differentiable, right? And now we know that as n tends to infinity, when you take the limit of tn's, so when you take the limit of these polynomials, the set of polynomials, you get that Taylor expansion. But in this case, you cannot do that because this function is finitely many differentiable. So that means that f is an element in n plus 1. See, n plus 1, that means f is n plus 1 times differentiable, right? So that's the problem. You cannot find the real Taylor expansion, but you can find a Taylor polynomial. So around this point, but there exists an error. That's so it is defined as r sub n of x. This is the remainder, right? So this is remainder is the difference between the actual function and the Taylor polynomial. So we are going to find the error bound of this remainder, the error bound over some interval around a, right? That's our idea. That's my idea, right? All right, now we want to find this error when you go away from this point. It is generate an error. So look at this one. If you substitute, if you plug a into here, into the equation, what happened to these terms? We know that t, when you plug a to the equation, so at this point, this Taylor polynomial is same with the function value at evaluated at a. So the distance between these two Taylor polynomial and the actual function at a is 0. Then r the remainder at a there is no error at the point a, right? So what about the first derivative of the remainder? Let's find the first derivative of that remainder. So the first derivative of this one, this cancel off, because when you differentiate a constant with a variable x with respect to variable x, this becomes 0. So what do you get? So when you differentiate this term, this turns out to be 1, right? And from other terms you get this factor x minus a. Then you plug the value a into that equation. So you see that other terms become 0 except this term, right? The first derivative of this this becomes is this one here, this constant. So let's do that. So t, the Taylor polynomial, nth order Taylor, first derivative of nth order Taylor polynomial at a is equal to this bit here, right? Other term, this bit here, f prime of a, right? Right, when you differentiate this one here, then plug the point a, then at the point, the first derivative of the remainder at the point is also 0. But we don't know other x's in around this interval. We don't know the error gap between f and Taylor, nth order Taylor, for other x's. So we are going to find that one, right? So now you can find this one also. The remainder, when you differentiate the remainder twice, also if you evaluate the remainder, so second derivative of the remainder at a, you will get 0, and third derivative also 0. This goes on until nth derivative. So when you differentiate the remainder n times, right, and substitute that point a, again you get 0, right? But we don't know about other x values. We know just only this point. So the all derivatives, this remainder term becomes 0 at this point. First nth derivative becomes 0 at this point. So we know that data, right?